In Chapter 6, we start to look at thermodynamics or thermochemistry, which is all about the energy involved in chemistry and in change. So, a lot of times we define chemistry as the study of matter and change. And in order for that change to happen, we either need to put energy in, or with some changes, energy will be released. There are several laws of thermodynamics that help to explain or at least state what happens in those changes. The nice thing is we won't need to know them by name, but just like Newton's laws with physics, with the first, second, and third law of motion, these laws really help us to understand where energy is coming from and where it's going to. And some terms hopefully we've seen and heard before, and maybe in a chemistry class or in a biology class, are the phrases endo and exothermic. Those are all about whether energy is entering or leaving, or whether we're making or consuming energy in a process. So exothermic is defined as energy flowing out of the process, the reaction, or more specifically, the system that we are studying. So the system is losing heat. It has less energy stored within itself at the end of the process. And very often we define exothermic processes as feeling hot. Endothermic is the opposite in all ways. Energy flows in. We take energy that used to be outside of our system of study, and now it is inside the system, sometimes stored as potential energy, or sometimes we think of it as chemical energy within our substances. As a result, these will often, and I have it backwards here, absorb heat. That's what happens. And they will feel cold, although a hot or a cold feeling isn't our only indicator. So a term that I used in those definitions was system. So system's somewhat a generic term, but it actually helps us to define what's going on here. So because in endothermic and exothermic, there's always heat going from one place and heat going to another place. And that energy that's leaving and the energy that's coming in are always going to be equal, and they're going to be opposite to one another in terms of the direction of flow or in terms of the gain and loss. In that case, it is important to understand what's the thing that we are really caring about. That is what we would call our system, or the object that we are observing, describing. Sometimes it's a chemical reaction, sometimes it is a physical object, sometimes it's a whole series of objects altogether. For example, we can think about ice cube being dropped into coffee from the perspective of each of those objects. We could think about the coffee as our system and study what's happening to the heat of the coffee, or we could think about the ice cube as our system and think about what's happening to the cube. In both cases, we would think about everything that is not that object or that system as the surroundings. So with that example, if the ice cube were the system, the ice cube is gaining heat from the surroundings. The coffee is hotter than the ice cube. Heat flows into the ice cube heats up, it melts, and it gains that heat. But from the perspective of the coffee, it is exothermic. It is giving its heat to the ice cube and probably a little bit to the cup and a little bit to the air. We have even more surroundings maybe to consider there. But with the coffee as the system, it is losing heat and it is exothermic. Both of those give good examples of how heat can travel. One way is by a temperature change. Heat and temperature are very closely tied together, but the definitions aren't exactly the same. Heat is a form of energy that flows because one thing is hotter and another is colder, or because of a difference in temperature. And what a difference in temperature means at the chemistry or atomic and molecular level is the measure of the average kinetic energy of the particles. So what's happening when we change temperature? We are changing the energy and therefore the heat content of the system. Those particles on average are speeding up as the temperature goes up or slowing down as it cools down. So in an endothermic, the system itself increases, and that would be because the surroundings go down in temperature. The particles within our system would likely be moving faster. The particles outside the system would be moving slower. And if we thought about how that would feel, it would feel cold because our hand, as we touch it, is actually a part of the surroundings. An exothermic reaction, the energy of the system decreases. The particles within the system were fast moving, and they transfer their kinetic energy through the flow of heat to the surroundings around it. The surroundings go up in temperature, a faster moving particles on average, or a higher average kinetic energy. And those exothermic reactions would feel hot because as your hand touches it, the heat transfers to your hand, and the hand would have an increase in the average kinetic energy of those particles. They would be higher, therefore, in temperature. As we thought about the coffee here, the coffee cooled down or decreased in temperature as it lost its heat. The ice also likely changed in temperature, but it also underwent a change in either phase or state. Those are sometimes used synonymously. Phase is slightly better of a term for that, although I kind of default to state out of old habits here. But in a phase change, we are changing not the speed of the particles, but we're changing how those particles are interacting with one another. In a solid ice cube, those particles are stuck more or less in place and just vibrating. But as the ice cube melts, the particles become a little bit more free moving. We are decreasing the attraction between the particles, often by increasing the average distance there. And we are overcoming we're not just adding heat to speed them up, we're adding heat to increase the potential energy between those particles. So this is important here. During that actual process, it's not getting hotter, but the heat is being used to change the phase. So with all of those, a real focus on system and surroundings, a flow of heat in and a flow of heat out, and a recognition of what that heat can do in terms of changing the spacing, the arrangement, the attractions, or very often with temperature, the speed of the particles.